Welcome back, Calculus 2 students. In this video, we're going to move beyond the arc length formula and parametric equations to a formula for the area of a surface of revolution. And so let's start by making sure we understand what that concept means. So suppose I've got a curve in the xy plane, and I'm going to take that curve and revolve it around the x-axis, or rotate it around the x-axis. So this point on the far left is going to rotate in a way that makes a circle, as will this point on the far right, and as will every other point that's in between them along the curve. And so we'll generate a surface in 3D space accordingly. And so what you need to make sure you understand is that we have a circle here that we're seeing from a skewed perspective. And likewise over here, that represents sort of the caps of this solid that we're making. Although it's not really a solid because it's hollowed out. So we might recall we made solids of revolution earlier and talked about their volumes. We're not rotating the entire region that you see here between the curve and the x-axis. What we're actually revolving is just the curve, or that segment of the curve itself. And so that's going to trace out this lamina, or this surface, and come back and close upon itself. All right, so what we'd like to do is find the area of that, the surface area of that surface. And we're going to look at it first in the context of a curve that's defined with parametric equations, x equals x of t, and y equals y of t, where t, as before, is ranging between, say, alpha and beta. And so what's the strategy for this? Well, as usual, we're going to break our curve into some segments. And let's just pick one of those segments right now, and let's think about what happens as that rotates around the x-axis. So if it only goes a little bit of the way, you can see how it's tracing out part of the surface in question. As we complete that rotation, let's turn it on its side. That segment is generating a particular type of shape. Now, if that segment is parallel to the x-axis, then you can imagine that what is being generated is going to be a cylindrical shape. However, it might be a bit of an angle, in which case, instead of the cylinder shape, what you're actually getting is part of a cone. It's actually called the frustum of a cone, a funny word. But basically it means that the top of that cone is cut off, and we're actually just focused on the bottom. So it's got two parallel sides. In our case, they're going to be circles, circular sides. So if we were in the simpler case of a cylinder, then we could figure out a formula for the surface area of that cylinder. And by the surface area, I mean just the lateral surface area. I'm not worried about the caps. So if you want to talk about the area of the surface, we're not going to be capping it where the blue and the red are. We're just going to be taking that little piece of the curve here for each segment that's wrapping around. And if we rotate that, tip it over, and get that cylindrical shape, one of the strategies for envisioning what is happening surface area wise is to take a pair of scissors and cut that and unfold it. And so on the one hand, we have the cylinder, and we have the area, the lateral area of the cylinder we'd like to understand. But also we have a rectangle of the same height as our cylinder, but the length is going to be the circumference of the cylinder. And you know that the circumference is 2 times pi times the radius. And so a formula for your area is 2 times pi times the radius times the height. So once again, that's going to be the area, the lateral area of this cylinder. So you can imagine like a soup can, and what we're talking about is the amount of area covered by the label. Okay, so if you have some brand name soup or is a generic soup and it's got a paper label wrapped around the can, you could unfold that label and that would be a rectangle, and that would give you the same area as the surface area of the can, or for the area that it covers. Okay, but that's just for a cylinder. It turns out for the frustum of a cone, it's pretty much the exact same formula, except instead of using the height, we're going to be using something related to this side length here. And so let's call that, for the moment, I don't know, let's say, let's call it ds, because that's actually what we're going to call it in our picture. Now, once we start thinking about very, very small pieces, we're not going to be worried about the difference between these radii. And so the area here is actually a little bit more complicated based on the fact that we have two different radii, but it ends up being related to that radius of that cone. And I'm not going to go into the details. I know that Stewart's textbook, for example, has a nice little segment that completely discusses this frustum. Our OpenStax book doesn't actually discuss this derivation at all. They just pop out the formula. But I'd like to give you a little bit of background where it comes from. And so if you pretend for the moment that what you're generating are cylinders, but you're doing so with a curve that's not quite parallel to the x-axis, you're actually going to look into the correct formula. And so let's kind of end this discussion and get right to that formula. Okay, so the area that we're going to be interested in is going to be the integral from t equal alpha to t equal beta. And so as before with the cylinder, we're going to have a 2 pi. And then we're going to have a radius. And I'm going to write in English in parentheses the word radius, because different scenarios are going to require different things to go inside these parentheses. And so 2 pi times the radius, that's kind of like a circumference. That's giving you the distance around. What we're missing is that analog for height. And instead of necessarily using a height as parallel to the x-axis, we're going to use the length of that segment. And from our arc length discussion, we know that that's going to be ds. And we have a variety of complicated and messy formulas for ds involving square roots, and we're going to go through those again in a minute in this context. But I want to make sure we're clear that we're going to have this radius, and I want to talk about the different scenarios that we're going to see where this radius is going to give us different functions. In our picture here, we have the radius as the distance between the curve and the x-axis. We know what that is. That is y. And so, in the example that we have over here, we can feel confident that y of t is going to give you the radius that we need. And then, of course, your ds, we can go ahead and write x prime of t squared plus y prime of t squared under a square root, and then dt. And so when you're first looking at this, this can be a little intimidating because it's got a lot of different parts. So I really highly encourage you to memorize this one right here, because it's going to be the most general, and as long as you know how to solve these problems from the perspective of building the pieces you need instead of memorizing formulas, this is going to serve you well. you don't want to memorize this or any of the others that I'm going to give you in this video. You want to memorize this idea right here and then figure out how to apply it. So 2 pi, in our case, it's the y of t that provides the radius, and then your ds as before. Okay, so let's look at a concrete example of this approach. I'm going to erase the picture and erase the formulas here, but I think I'll copy down this formula up top right for reference later. So we have the area, and then we have an integral. And I think I'm even going to leave these guys right here undefined because there'll be times when we want those to be t values or x values or even y values. So I'm going to leave those sort of open. Maybe I'll put some boxes just so we don't think it's an indefinite integral. So we're going to have an integral, and we have 2 pi times the radius, and then ds. Okay, so that's the general idea. So what if we have given to us x equal to 2t and y equal to t cubed with t ranging from 0 to 1. And so this is going to be a parametrically defined curve, and we'd like to find what happens when we rotate that curve about the x-axis, what kind of a surface we get. In particular, what is the area of that surface? So let's write out that question formally. Find the area of the surface generated by revolving the curve about the x-axis. And so if we're revolving around the x-axis, then this is going to be, as we discussed before, the y value, just like in our picture. And so let's have a look at that. We'll have the x prime of t is 2, y prime of t is 3t squared. And so we need to compute the integral from t equals 0 to t equals 1, 2 times pi. Now we need the radius, and that's given by our y value. Whoops, that is not the y value. That was y prime, I miscopied. So 2 pi times t cubed, and then we need our ds. And our ds consists of x prime squared plus y prime squared under the square root, and then dt. So let's simplify what we have under the root, and we'll go ahead and combine this as well. So 2 pi t cubed, and then we have a square root of 4 plus 9t to the 4th dt. We can evaluate this integral using a basic substitution. So if we were to let w equal 4 plus 9t to the 4th, then dw would equal 36 t cubed. And so dw over 36 would be t cubed. And as t is ranging from 0 to 1, w then is going to be ranging from 4 to 13. And so the integral in question is going to now be rewritten as the integral from 4 to 13 of, so now what do we have? We have a 2 pi times t cubed, where t cubed is dw over 36. So that's pi over 18 with a dw on the end. And then under the radical, we just have w, so I drew that quite ambitiously. That was not needed. And so we'll have w to the 1/2 dw with a constant in the front. And so that's pretty easy to anti-differentiate. We just need to multiply by 2/3 because we're going to have w to the 3/2 as our antiderivative. and evaluate from 4 to 13. And so in our case, we're going to get pi over 27 times 13 to the 3 halves minus 4 to the 3 halves. And while 4 to the 3 halves is 8, and so that's kind of nice, 13 to the 3 halves, not so nice. And so we'll leave that alone. So there's a demonstration of how to use the surface area formula given for parametric equations. But there are a couple different varieties of this that we ought to explore. So if we are going about the x-axis, as we did a moment ago, then just like I wrote earlier, we're going to have this formula, 2 pi times the y value, and then ds. And ds can be that big, nice square root. And we can go ahead and do that. X prime of t squared plus y prime of t squared dt. But, so this is if you're going about the x-axis. If you're going about the y-axis, however, then your height, your radius is no longer the y value. If you're going to rotate this way, you're going to be looking for the distance between your curve and the axis of rotation. That's going to be a horizontal distance, and that's going to be given by the x-coordinate of your point. And so in those situations, you're going to want 2 pi times x of t, and then ds. And in this case, the ds is identical to before. Okay, and so we're just starting to get into the variety you might see, but once again, we're going to have a couple more formulas here. It's better to remember this general formula and then figure out what is the radius in your situation. In reference to the previous video, I want to consider what happens when y is given as f of x. No t, no parametric. So what are we going to do there? If we're going to go about the x-axis, we're going to evaluate, let's say, between some x values, like x equal a and x equal b. We'll still have 2 pi. And once again, the y value, which is given by f of x, is going to be your radius. Your ds comes next. And in this situation, remember, it's 1 plus the derivative of f of x squared dx. On the other hand, if you're going to rotate or revolve around the y-axis, then we don't have to actually reconfigure this all in terms of y. If we are given the information in terms of x, we can still use the exact same format for ds, that ugly square root right there. But what has changed is that radius, and once again it's x, and we could just write the letter x there. And so this would be the integral format we would use there. Of course, you have more varieties of this where it's more convenient to integrate with respect to y, with a dy and y values. And so you might have a 2 pi y or a 2 pi g of y, depending on the situation. So rather than demonstrate 6 different formulas completely, I always want to come back to this guy right here. Can we conceptually understand the building blocks that go into it, and then explore our particular problem to figure out what these values mean for us?